welcome to another video on my channel. Today we will be talking about the basic trigonometric function derivatives, how to apply them, and how to prove each of them exist using the limit definition of the derivative. The goal is that you guys will be able to do the four things below. Number 1, derive trigonometric derivatives using limit definitions. Number 2, apply the basic derivative formulas. Number 3, solve some problems. And number 4, also combine these with basic algebraic functions for a deeper level of understanding. Now, a quick review. The definition of the derivative, the limit definition of the derivative is f dash of x or dx or dy by dx is equal to limit as h approaches 0 of f of x plus h minus f of x divided by h. And there are two key trigonometric limits we'll need, plus one more that I'll cover later. The first one is limit as h approaches 0 of sine h over h is equal to 1. The second one is limit as h approaches 0 of cosine h minus 1 over h is equal to 0. Here are all the steps to derive the limit definition of the derivative of sine of x. So, what it is we have, starting off with d over dx of sine x is equal to limit as h approaches 0 of sine x plus h minus sine x divided by h. Then, using the angle addition formula, which we covered last video, or really it wasn't really a coverage, it was more so a review, just to prepare you guys for this so you weren't surprised when I started using this. So, the angle addition formula says sine of x plus h is equal to sine x cosine h plus cosine x sine h after some substitution and simplification, where what we do is the first part of sine x plus h, which is sine x cosine h, and the negative sine x will be part of one part of the problem. So basically what we're doing is we're kind of splitting up the fraction. That's why there's h on the denominator over here. Then what happens after that, the second part is the second part of the sine x plus h identity or function itself. So that becomes sine x multiplied by, and the reason it's sine x multiplied by is we factored it out, multiplied by cosine of h minus 1 divided by h plus cosine of x times sine of h over h. Now this is equal to sine of x times 0 plus cosine of x times 1 is equal to cosine of x. Therefore, d by dx of sine x is equal to cosine of x. The strategy to find the limits of cosine of x is in fact quite similar. What we're going to do is we're going to start with the limit definition of the derivative and substitute cosine of x instead of f of x. So we have cosine of x plus h minus cosine of x over h, of course, as the limit of h approaches 0. Then, using the cosine angle addition formula, cosine of x plus h is equal to cosine x cosine h minus sine x sine h, and using the splitting form or factor or the method that I covered in the last one, where it is cosine, the first part of the cosine x plus h or sine x plus h or whatever it is, whatever function it is, what happens there, we do that and negative cosine of x, and then the other part is negative sine x sine h. Of course, both of them have to be divided by h. Then what happens is we have cosine of x times 0 as the limit shown above, so the limit of cosine h minus 1 divided by h minus sine x times 1. Now, if you're wondering how all these limit formulas hold, like the addition, the subtraction, you can look, or if you're wondering how they're even there, you can also look at my Intro to Calculus series, which covers pretty much everything related to limits. So, in the end, it becomes negative sine of x. So the derivative of cosine of x is equal to negative sine of x. For the derivative of tangent of x and the derivative of the next three functions beyond, what is going to happen basically is the fact that I will not be showing all the simplification process as it starts to become quite apparent, and a sort of challenge or exercise for you is to figure out that algebraic manipulation yourself, as it will further increase your skills. Instead of you just relying on me to prove it for you, you can also, with the same framework I showed you above, prove it yourself. So, using the limit definition, we get tangent of x plus h minus tangent of x. Then we do use the tangent addition formula. Then the third limit comes in. Limit as h approaches 0 of tangent of h over h is equal to 1. And 1 plus tangent squared x is equal to secant squared x, which is something known as a Pythagorean identity in trigonometry. Now, I told you you can do the algebraic manipulation yourself, following a similar framework of what I did above. So, therefore, d by dx of tangent of x is equal to secant squared x. Deriving the derivative of cotangent x also uses another limit, and so will the others. So, pretty much every slide from tangent of x and afterwards has the few slides, and the reason I didn't include it for the first one is also because I showed the first two, is because I showed all the steps for the first two, and also I just wanted to make it clear because those are pretty much the two most foundational limits that you can use to derive all the rest of the limits that I'm showing below. So, using the limit definition, we get cotangent of x plus h minus cotangent of x over h. Then, using the tangent addition formula, and you might be confused, how is it tangent? But you need to remember also the fact that there's no cotangent addition formula, at least not that I'm aware of, and cotangent is equal to 1 divided by tangent. So, if you're clever enough, either you could do it in your head or you can do it on your piece of paper. It will resort to some of the limits shown over here. So, and another Pythagorean identity that we're going to use is 1 plus cotangent squared x is equal to cosecant squared x. Then, after algebraic manipulation, what happens is d by dx of cotangent of x is equal to negative cosecant squared of x. Now, deriving the derivative of secant of x is actually quite similar to what we were doing earlier, except now I decided to just show you after we substituted secant of x is equal to 1 divided by cotangent of x. 1 divided by cosine of x. Cotangent and cosine are two different functions. But since I'm doing that, then I already decided to show some of the simplification, thus removing the need for complexity for that. Then, using the cosine addition formula and our standard limits, we'll end up with sine x over cosine squared x is equal to secant of x, tangent of x. Then, that means, therefore, d by dx of secant of x is equal to secant of x, tangent of x. And the final derivative that we need to derive is cosecant of x. So, using the limit definition to find this, and also substituting cosecant of x is equal to 1 by sine of x, we get limit as h approaches 0 of sine of x minus sine of x plus h divided by h sine of x plus h. Then, using the sine addition formula and our standard limits that we covered above, so what I mean by standard limits is the standard limits we covered all the way above, we get negative cosine x over sine squared x. That means it's negative cosecant x cotangent of x. Therefore, the derivative of cosecant of x is equal to negative cosecant of x cotangent of x. Before we go on to solve our examples for the day, let's have a quick summary of all 6 trigonometric derivatives. So, the key formulas are d by dx sine of x is equal to cosine of x, d by dx cosine of x is equal to negative sine of x, d by dx tangent of x is equal to secant squared x, d by dx cotangent of x is equal to negative cosecant squared x, and d by dx secant of x is equal to secant of x tangent of x, and the final one, d by dx cosecant of x is equal to negative cosecant of x cotangent of x. So those are the 6 formulas you can memorize, or but I also think it's better to have it memorized and understand the underlying proof, because it might prove to be useful having that insight in the future with maybe more complicated problems. The quick memory aid is the cofunctions cosine, cotangent, and cosecant have negative derivatives, while sine, tangent, and secant of x have positive derivatives. The first example is to find the derivative of f of x is equal to 3 sine of x plus 2 cosine of x minus 5 tangent of x. Now, the point is to use the basic derivative formulas, and a hint is that the derivative of a sum is the sum of derivatives, and constants can be factored out. Things that were discussed in one of my previous videos and also proved using limit identities or limit formulas, and the limit definition of the derivative. Now, you might wonder, I keep coming back to the limit definition of derivative. It's because the limits and the limit definition of derivative in specific are so foundational to how we view derivatives and everything that I think it's really necessary, and I can really not stress it enough that it's extremely important to understand that and how it works, as it will definitely provide you really good insights in the future. So, let's get started on the problem. Right now, our problem is f of x is equal to 3 sine x plus 2 cosine x minus 5 tangent. So, what we have of x is equal to 3 times the derivative of sine of x, or if we want to be traditional, we can say f dash of x is equal to d by dx of 3 sine plus 2 cosine of x minus 5 tangent. Now, what one of the derivative identities is that plus, if we have plus or minus, we can split that up into different derivatives. So this is equal to d divided by dx of 3 sine of x plus d over dx of 2 cosine x minus d by dx of 5 tangent of x. Even though it cannot show over there, it should be able to copy down over here, and those are our first couple of steps. Now, I will normally not go into this much detail, completely splitting apart step by step. I'm just using it for this problem to show all of the identities and formulas in motion, and to show you how building a constructive understanding and layering concepts on top of each other, in fact, leads to something much, much better than just average having a cheat sheet or memorizing things. So, our next step is to factor out all the coefficients. So we have d by dx of 3 sine of x, so that'll be 3 times d by dx of sine of x plus 2, then d by dx of cosine of x minus 5 times d by dx of tangent of x. Now, what we can do over here is we can just evaluate each of the trigonometric derivatives according to the formula above. The formulas, not just one formula. There's 6 of them. So, 3 times cosine of x for sine of x minus 2 times sine of x. Even though it has plus over here, the derivative of cosine of x is negative sine of x. Then, the derivative of tangent of x is secant squared x. So, we have negative 5 times secant squared x. And that is precisely our answer. F dash of x is equal to 3 cosine of x minus 2 sine x minus 5 secant x. Secant squared x. Now over here, I'm just doing a little bit of formatting to make it look a little professional. But over here is the final answer. It's going to be slightly bigger than the rest to show that this is our final answer. When we move on to our solution, it shows the exact same thing. The answer is that f dash of x is equal to 3 cosine of x minus 2 sine of x minus 5 secant squared x. The next problem is to find the derivative of g of x is equal to minus 4 cotangent of x plus 7 secant of x. Now, the plan is to pretty much do the same as we did for the previous problems. So, what we're going to have is we're going to have g dash of x is equal to d divided by dx of 4 cotangent 7 secant of x. So, what happens over here is, after that, we can quickly simplify. So, after removing the coefficients from everything and factoring and basically splitting it, so it'll be d by dx of 4 cotangent of x plus d by dx of 7 secant of x, we get d over dx of, 4 times d over dx of cotangent of x plus 7 d over dx plus 7 d over dx of secant of x. This is going to be pretty much all the simplification we need to do, because after that we can quickly find the derivative by evaluating each of the derivatives individually. So for the derivative of cotangent of x is negative cosecant of x squared. So it'll be negative 4 times cosecant squared x plus 7. Now the derivative of secant of x is secant of x tangent of x. So we have 7 secant of x times tangent of x, and that will be our final formula over here. This will be the final answer that we get for this problem. And over here, it shows the same thing for the solution. Now, I stated this many times before. This slide is pretty much always for the people who just want to skip ahead, don't want to fit it all around, just want to find out the solution, because either they're faster than me explaining it, or they pause the video and decide to do it themselves without waiting for any of my explanations, and that's perfectly fine as long as you're learning in the process. The final problem is actually probably my favorite example, because it involves not only the trigonometric derivatives, but also just the identities of derivatives and also the power rule. So it's 2 rules in one problem, but it's not using any concepts that we haven't covered yet. But when we cover stuff like the product rule, the chain rule, implicit differentiation, things can start to layer onto each other, and it can get very complicated very fast. But for now, since there's not as many topics, it's going to stay a little bit simpler. So we can start with saying h dash of x. Now I'll skip a few steps because I showed you like d over dx of this, d over dx of that. So I'll just go straight into the full simplified form before we start substituting. So 2 times d by dx of cosecant of x minus 6 times d by dx of sine of x plus d by dx of x cubed. This is the first step in the problem, or really I skipped a few steps because I showed you some of the previous steps, and doing it again and again can get repetitive and normally will not teach you much. But when you're solving a problem on your own, make sure also to double check your work, and a good way to do that is also by stating out every step, so it's easy to figure out where your mistake is and redo it from there. The next thing that we're going to do is we're going to finally evaluate it. So d by dx of cosecant of x is negative cosecant of x cotangent of x, and since there's a negative because it's negative cosecant of x cotangent of x, and it was positive earlier. Now d by dx sine of x is equal to cosine of x, which was covered in the formulas above, but there was nothing special about that, no negatives, so it stays as negative 6. And according to the power rule, the derivative of x cubed is 3x. The answer to this problem is h of x is equal to 2 cosecant of x cotangent of x minus 6 cosine of x plus 3x squared. And over here, here's the solution. The answer is, as I said earlier when I was explaining the problem, h dash of x is equal to negative 2 cosecant of x cotangent of x minus 6 cotangent of x plus 3x squared. And over here, people can also see some of the more simplified step-by-step breakdown of what I'm doing over here, but with the added disadvantage as I'm not exactly explaining every step verbally. So if you prefer to learn by doing, just reading it, feel free to skip ahead into this slide, this area, and mostly skip my explanation to understand how it works. If you'd rather see all the steps, are okay with me not explaining it. Now, here are a few practice problems and solutions. So the first few there's 5 practice problems I have for you. The first one is 2 sine of x plus 3 cosine of x minus tangent of x. The second one is 4 cotangent of x minus 2 secant of x plus 5 cosecant of x. Then the third one is d by dx of x cubed plus 2 sine of x minus 4 cosine of x. The fourth one is d by dx of 5x squared plus tan x minus cotangent of x. And the fifth and final one is d by dx is equal to 3 secant of x plus cosecant of x minus 2x. And all of the solutions are on the right if you want to check your answers. I'll probably start doing this for all the future videos, including the solutions right there, so you don't have to search it up or just try and double guess yourself. And here is a small quick review. All of the 6 basic trig derivatives derived from limit definitions, that's what we did above. Then the cofunctions, cosecant, cotangent, cosine, even though it's in the exact opposite order written over here. If we said it in the order it was written, it would be cosine, cotangent, cosecant. All of them have negative derivatives. The limit definition helps us understand where these formulas come from and can also aid in application. And you can combine with the power rule for polynomial terms and linear combinations follow the sum rule for derivatives. And the sum rule for derivatives, the subtraction rule for derivatives, the coefficient rule for derivatives, the constant rule for derivatives, all of these were covered in another one of the videos in my calculus series. So, and linear combinations are just like, if we have a linear combination of x and y, it can be like 2x minus 3y, 18,750x minus 1.3 times 10 to the 18 multiplied by pi multiplied by y, as long as it's like a coefficient times x plus or minus a coefficient times y would be a linear combination of x and y. Thank you so much for watching this video. It really helps a lot when you guys watch the video to the end. It really helps a lot when you guys watch videos, my videos in general. It really means a lot to me to know that people are getting educated from this, because quite frankly, the school system doesn't do a good job of explaining this and often kills students' curiosity and in fact leaves them with a worse understanding whether if they would actually have went on YouTube or found a good mentor. So this is the goal of this channel. Like, subscribe, and hit that notification button if you like these videos. Of course, there's no obligation, but it's always appreciated. And please make sure to comment down below any suggestions, tips, or questions for the channel. I'll answer pretty much everything besides like personal questions like age, school, location, etc., and name. But besides that, pretty much all questions are open. So thank you so much. See you in the next one, and bye-bye.